So our next topic is power and bandwidth calculation of AM for multi-tone modulating signal. So we have calculated the power and bandwidth and power saving for amplitude modulated signal and its type. So let's see if the message signal is having more than one frequency component, then how we can calculate the power and bandwidth. So the message signal is a multi-tone signal. So multi-tone modulating signal MT is, let's write A1 cos 2 pi F1t and A2 cos 2 pi F2t. This is our message signal and it is having more than one frequency component. That's why it is called multi-tone modulating signal. And the expression of amplitude modulated signal in general is given by AC 1 plus K into MT cos omega CT. This is the expression of amplitude modulated signal. So this message signal is a multi-tone signal. So substitute this value of MT in this equation. We get S of T equal to AC 1 plus K into A1 cos 2 pi F1t plus K A2 cos 2 pi F2t and cos 2 pi FCT or omega CT. So we know that the modulation index is defined by K into maximum value of MT. So here the maximum value of MT is corresponding to each frequency component A1 and A2. So corresponding to this frequency component F1, the maximum amplitude is A1 and its amplitude constant is Ka. Its amplitude is A2 and amplitude modulator constant is Ka. So this K into A1 is 1 plus MA1, modulation index corresponding to frequency F1, cos 2 pi F1t plus MA2 cos 2 pi F2t into cos 2 pi FC into T. So we know that if the amplitude modulator block is constant, then its amplitude sensitivity will remain same. If we change the message signal, the K will remain same. Like this, we have seen that if we have amplitude modulator, and we give the input signal MT, and another signal is AC cos omega CT, we get AM signal. But the sensitivity is Ka. So we are changing this message signal. This message signal previously it was a single tone modulating signal. Now it is a multi-tone modulating signal. So the block is same, the message signal is we are changing. So the K is constant for both the signal. So that's why we are getting the modulation index K into A1 corresponding to frequency F1 and K into NT corresponding to frequency F2. Now if we multiply this, we get AC cos omega CT and cos A cos B, 1 by 2 cos A plus B and cos A minus B. So we get AC MA 1 by 2 cos A plus B, so cos A plus B will be 2 pi F1 plus FC, or you can write FC plus F1 because carrier frequency is having higher frequency than F1 plus AC MA2 by 2 cos 2 pi FC plus FC minus F1t and if we multiply these two, we get cos A plus B and cos A minus B again. So this is the frequency Fc and this is the frequency F2. So we get, let us write here, plus AC Ma2 by 2 cos 2 pi Fc plus F2t plus AC Ma2 by 2 cos 2 pi Fc minus F2t. So this is the total expression of amplitude modulated signal if we have two frequency component in our message signal. It may be more than two, because more than one is called multitone. We are assuming up to two terms because we have to take the more number of terms if we consider more number of frequency component in message signal. So we are assuming only two components, that is F1 and F2. So this is the carrier signal, this is upper sideband, this is lower sideband, and this is second upper sideband and second lower sideband. Now we have to transmit this signal S of t. So if we want to transmit this signal S of t, the power will be, the total power Pt is the power required for each term. So this is the first term, AC cos omega Ct, and the power required to transmit this AC cos omega Ct will be AC square by 2R, plus power required to transmit this term we have calculated already. This is AC square Ma1 square divided by 8R, amplitude square divided by 2, plus, and the upper sideband and lower sideband having the same amplitude, that's why this will be Ma1 square divided by 8R. This is first upper sideband and first lower sideband power. Similarly, this is the first, second upper sideband, second lower sideband, and its amplitude is AC Ma2 by 2. So the amplitude square divided by 2R is AC square Ma2 square divided by 8R plus AC square Ma2 square divided by 8R. So this is the total power. Now this is known as carrier power. So if we represent all the terms in terms of carrier power, then we will get Pt equal to Pc, means we are representing AC square by 2 equal to Pc. So this is Pc and this is Pc Ma1 square divided by 4R plus Pc Ma1 square divided by 4R plus Pc Ma2 square divided by 4R, and this is Pc Ma2 square divided by 4R. So if we add all this, we get Pc common and 1 plus, in this 2 Pc is common and we have Ma1 square, sorry, this not, there will not be R because we have considered it in Pc. So we get Pc common, then Ma square by 4 plus Ma square by 4 is Ma1 square divided by 2, plus here also we have taken Pc common, so Ma2 square divided by 2, or we can also write Pc 1 plus Ma1 square plus Ma2 square whole divided by 2. So this is the total power required to transmit these two signals. As we can see that this is nothing but in the form of the power required to transmit AM signal for single tone modulating signal. For single tone modulating signal, the power requirement is Pt is equal to Pc1 plus Ma square by 2 for single tone modulating signal, and here we are getting Pc1 plus Ma1 square plus Ma2 square. Here it was Ma square because there were only one frequency component, that is FM, and corresponding to FM we get one modulation index. Here we are getting two modulation index square because here we have two frequency component F1 and F2. So we can write this total power in this form: Pt is equal to Pc in bracket 1 plus Ma total square divided by 2. In this way we can write. So here MA total is root over MA1 square plus MA2 square. So in general, if we have more than one frequency component, we can calculate the total power in a similar way as we have calculated for single tone modulating signal. And in general, we can write, if the message signal is in the form A1 cos 2 pi f1t plus A2 cos 2 pi f2t and so on up to an, suppose nth term, an cos 2 pi fnt. Suppose we have n frequency component, then total modulation index MA total will be root over, corresponding to this frequency component we get one modulation index MA1 square, corresponding to this frequency component we get another modulation index MA2 square and so on, and corresponding to nth frequency component we get another modulation index MAN square. So this is the general formula for total modulation index. And transmission efficiency in general, for single tone modulating signal it was transmission efficiency. For single tone modulating signal it was MA square upon 2 plus MA square. So here we can write transmission efficiency as eta is equal to, which is the ratio of total sideband power divided by total power, MA total square divided by 2 plus MA total square. This is the transmission efficiency, and remember this, these all we are calculating is just for a sinusoidal modulating signal. We have considered the message signal as sinusoidal signal. One more thing that you can calculate is the sideband power and the carrier power, ratio of sideband power and carrier power for single tone. For single tone we are writing here, for single tone sinusoid signal, this is the total sideband power was PC MA square by 2 and the carrier power is PC, so we get MA square by 2. So the ratio of sideband power to carrier power is MA square by 2 if we consider message signal as single tone sinusoidal message signal. In general, we have expression of AM S of t is equal to AC 1 plus KMT cos omega CT. And if we calculate the carrier power, we get AC square by 2 if we take R equal to 1. And the sideband power we have calculated, which is AC square by 2 K square M square T bar or mean square value, which we have written AC square by 2 K square into SM. So this is the sideband power. So in general, if we calculate this ratio, sideband power to carrier power, so sideband power to carrier power is AC square by 2 K square into SM, which is message signal power, divided by AC square by 2. And this AC square by 2 and AC square by 2 will get cancelled, and we get sideband power to carrier power is equal to K square into SM. So all the message signal power is actually proportional to amplitude square, amplitude of message signal square, because if we calculate power, then we know that this message signal is 1 upon t integration over the time period m of t magnitude square dt. So it means that the power is directly proportional to the amplitude of message signal, square of amplitude of message signal. So this message signal is proportional to the square of amplitude of message signal. So the message signal power is proportional to square of amplitude of message signal in this form. So this is K, this is AM, and modulation index is defined by K into maximum value of MT. This is modulation index. So any message signal, and we have considered that the peak amplitude of this message signal is AM. So for any message signal, K into AM gives modulation index. So multiplication of K into AM gives modulation index, and we are having square of these two. So we get the ratio of sideband power to carrier power is proportional to MA square. So in this way we can say that the ratio of sideband power to carrier power is directly proportional to MA square, but for sinusoidal signal it is MA square by 2, but in general we can say it is directly proportional to MA square. So if the question is asked that if we increase the modulation index by factor 4, then the ratio of sideband power to carrier power is increased by, then we can say that the modulation index is increased by factor 4, then the 4 square will be 16. So this ratio sideband power to carrier power will be increased by factor of 16. So in this way we can calculate the transmission efficiency for multitone, and this ratio is also important because sometimes the question is directly asked that the ratio of sideband power to carrier power. If it is sinusoidal, you can directly use this formula, and otherwise you can calculate this relation by this ratio by this relation. Sideband power to carrier power is equal to K square into power of message signal. Whatever will be the power of message signal, you can substitute this here and you get this ratio sideband power to carrier power. So next we have to see the bandwidth of AM signal for this multitone modulating signal. So bandwidth requirement, that means we have to transmit this signal S of t AM signal, and to transmit this signal what will be the required bandwidth, and for that we have to take Fourier transform of this expression S of t. So we know that these all are having the cosine component, and the Fourier transform of the cosine component is impulse, and the bandwidth is calculated from one side of a spectrum. That's why we are drawing only one side of a spectrum. So we have this S of f, this is f. If I take Fourier transform of this cosine signal, then we get impulse at plus minus fc, because cosine is having Fourier transform which is given by cos omega ct is 1 by 2 del f minus fc plus del f plus fc. This is the Fourier transform of cosine signal. So at fc we will get some amplitude. Amplitude is not important here because we are more concerned about bandwidth of the signal. So the amplitude is important for power calculation that we have already derived. So in case of bandwidth calculation, there is no importance of amplitude of this impulse. Still we can write, because this is 1 by 2 times and the amplitude is AC, so we can write AC by 2. So here the amplitude we can write AC by 2. I am not drawing the negative part, but negative part of a spectrum will be present there. And now next component we have is at fc plus f1. Cos 2 pi fc plus f1, it means if we take the Fourier transform we get impulse at frequency fc plus f1. So this is the frequency fc, and we have to add some small frequency because the carrier frequency is much higher than the message signal frequency. So this frequency is fc plus f1. This is small frequency we are adding, and this will be the having amplitude AC MA1 by 4. Now next component is fc minus f1. So fc minus f1 we will be having another impulse at frequency fc minus f1. So this will be the another frequency fc minus f1. Impulse at fc minus f1. Now next component is cos 2 pi fc plus f2. So if we take the Fourier transform, we get impulse at frequency fc plus f2. And fc plus f2, there are two frequency component f1 and f2, so one will be higher than other. So we are assuming that the frequency f2 is greater than f1 because both are different, so one will be greater than other. So we are assuming f2 is greater. So if f2 is greater, then if we add the f2 in fc, we get impulse at fc plus f2. This height can be more than this amplitude, but it depends on the value of modulation index, because AC by 2 is common in both the term. AC by 2 is common in both the term. MA2 and MA1, here it will be MA1, here it is MA1. So MA2 and MA1 will be different, and the MA2 value can be greater than MA1, but here I am considering this MA2 is less than MA1, that's why the amplitude is less than compared to this. So this is FC plus F2, and because of this term we get FC minus F2. So FC minus F2, the same frequency which we have added, we have to subtract it and we get FC minus F2. So the bandwidth required, or you can write amplitude here also. So the amplitude will be AC MA2 divided by 4. AC MA2 divided by 4. So the bandwidth will be highest frequency component and lowest frequency component. This is 2 times of F2. 2 times of F2. And the bandwidth is 2 times of F2, and because the F2 is greater than F1, the spectrum is extended up to F2, FC plus F2. If there are more frequency component and whatever will be the highest frequency, the spectrum will be extended up to carrier frequency plus that higher frequency. Suppose I take another frequency component like AC cos 2 pi F3t, and we assume F3 is highest. F3 is greater than F2 and F2 is greater than F1. That means F3 is highest frequency. And if we take the Fourier transform, so we get the spectrum at FC plus F3 somewhere here, and another FC minus F3 somewhere here. So in that case, FC plus F3, and this is FC minus F3. So bandwidth would have been 2 times F3. If there are 3 frequency component and the third frequency component is highest frequency, then we can draw the spectrum in this way, and in that case the bandwidth is 2 times of F3. So what we observe is whatever will be the highest frequency, the spectrum is extended up to that part, and the resultant bandwidth is 2 times of that highest frequency component present in message signal. So the frequency component present in message signals are F1, F2, F3. The highest component previously it was F2 only, then bandwidth was 2 times of F2. Now we have considered the third frequency component, now the F3 is highest, then the bandwidth is 2 times of F3. It means that in general we can say that the bandwidth of AM signal for multitone modulating signal is twice of maximum frequency component present in MT. So in general we can write bandwidth in general 2 times of maximum frequency component present in message signal. Bandwidth is 2 times of maximum frequency component present in MT in general. So this is all about the power and bandwidth calculation of AM for multitone signal. Now we will see the workbook questions.